Definitions, formulas, and basic concepts. This section is a review of definitions and terminology. We will cover the terms typically used when dealing with energy and power, keeping with the focus of this class, a small system approach. As stressed earlier, the number one priority is, and has to be, the permit. Also, regardless of what changes we think we can make in a plant to save energy, they cannot be made without first completing a thorough evaluation on how the change might affect the process. We have to look at our individual situations because every situation is slightly different. Some definitions we should know. Watts, or W, equals volts multiplied by amps. Anybody with an electrical background knows it is a little more technical than that, but nonetheless, fundamentally, it is the product of volts multiplied by amps. Kilowatts, or kW, 1 kilowatt equals 1,000 watts. On our electric bills, we are billed for the kilowatt hours we use. Kilowatt hours, or kWh, kilowatts multiplied by hours equals the amount of energy we are using in kilowatt hours. 1 horsepower, or HP, equals 746 watts, or 0.746 kilowatts. Recognize that there is a relationship between horsepower and kilowatt that we need to understand. Our focus today will be equipment. It is going to take motors to run the pumps. It is going to take motors to run blowers. So we deal with motors. Duty cycle. Number of hours a motor is running per day or per month. We want to know this information on each piece of equipment in order to access the cost to operate. Load factor. Measured or assumed percentage of full load amps. When talking about load factor today, we are talking about a measured or assumed percentage of the full load that we are dealing with. In other words, if we have a motor nameplate that says 20 amps and we are drawing 20 amps, it is running at full load or its load factor is 100%. Energy Conservation Measure, or ECM. This is any action taken to save energy. For the purposes of this training, we are going to call that an Energy Conservation Measure, or ECM. This table is a good summary of formulas that can typically be used to determine kilowatt, amps, power factor, and horsepower. Let's take a look at the kilowatt formula. I multiplied by E divided by 1,000. When we are dealing with direct current, I is amps, E is volts. So with direct current, kW equals volts multiplied by amps, which when divided by 1,000 equals kilowatts. In direct current circuits, let's take a look at watts. W equals I multiplied by E. Watts equals amps multiplied by volts. With alternating current, or AC circuits, if it is a single-phase circuit, I multiplied by E multiplied by PF divided by 1,000. The formula is amps multiplied by volts multiplied by a power factor, then divided by 1,000. This power factor, or PF, basically shows us how effectively we are using the power that the power company provides. A load with a low power factor draws more electrical current than a load with a high power factor for the same amount of useful power provided. This is not about efficiency. It is about how effectively our equipment is using the power that has to be at the electrical pole to provide us with the electricity we need. Just keep in mind that a perfect power factor is 1. Anything less than 1 or more than 1 means there is something that is a little out of balance. However, our power company can penalize us for having a poor power factor because we are not effectively using the power they must have available for us. Most of the time, we are going to be at some value, probably in the zero point 0.8 to zero point 0.9 range. As an example, while we have single-phase equipment out there, most of the equipment for power consumers are the three-phase. The three-phase formula for kilowatts is 1.73 multiplied amps multiplied by volts multiplied by the power factor, then divided by 1,000. So that's 1.73 multiplied by I multiplied by E multiplied by PF divided by 1,000. What is the 1.73? Simply, if we take the square root of 3, which is a three-phase power, the answer is 1.73. Now, the significance of that from a troubleshooting perspective is whenever we lose power on a power leg, we call that single phasing. Then the amperage on the other two phases goes up by a factor of 1.73. Reading a motor nameplate. We are a small system and we are going to have to do what is called a desktop evaluation on this piece of equipment. In order to do a desktop evaluation, we need to be able to read and make sense of our motor's nameplate. All motor nameplates have the same basic pieces of information on them that we need to understand. Another reason we need to know some of this information is because if we are thinking about replacing a motor, we want to do the best we can to replace it with another motor with the same standards that have already been evaluated. Some information found on this nameplate includes ENCL-EPFC. This describes the type of motor, telling us it is an explosion-proof fan-cooled, or EPFC, motor in an enclosed environment, or ENCL. Next, we will see a frame number. The frame designation is important because the frame number ensures the bolt holes align the same, and the shaft size and keyways are the same. Matching the frame numbers ensures that we do not need to make a lot of other changes when changing out a motor. In this case, we can see this is a three-phase motor, 60 Hertz, 25 horsepower that equates to 18.7 kilowatts. Let us do the math and see if it works. 25 horsepower multiplied by 0.746 kilowatts per horsepower equals 18.7 kilowatts. Yes, it works. The nameplate must be reliable at this point. We can see that this motor is running at 1,774 revolutions per minute. If we go to replace a motor, why is speed important? Think of something we might put a new motor on. Why would you be worried about the speed? For example, if we have a pump that is spinning at 1,700 revolutions per minute, or RPM, and we speed it up to 1,800 revolutions per minute, what are we doing? We are increasing the flow and changing the load or horsepower requirements on that motor. We need to understand that we cannot ignore the revolutions per minute when we change out a motor. We have to try to be close, because this has already been thought about in the design. With the pump, we need to be careful about changing speed, because flow and horsepower are related to speed. The nameplate also has the motor's full load efficiency, or EFF. If we are dealing with a newer plant, we probably have the newer energy-efficient motors already in place, so it is likely we will find our only ECM opportunity will involve the way we operate that equipment to save energy. If we have older motors around, a desktop evaluation, like this, is an excellent way to evaluate those motors. Most of the newer motors today are already very efficient because of the new electrical standards. We can see that this nameplate is for a 460 volt motor with 31 FLA. FLA stands for full load amps. This means that if this motor is using the full 25 horsepower, it is going to have a full load amps draw of 31. From a desktop perspective, if we are currently drawing half of that, 15.5 amps would be how much horsepower we are currently using. So the full load is 31 and we are using and need only 15.5. Then we are using about half of the horsepower available. If we were to do actual measurements, it may be slightly different. But for our desktop evaluation, it is easy enough for us to determine that if we have half the amps of what it says on the nameplate, then we are using half the horsepower. So now we have an opportunity to consider changing the horsepower. Maybe we do not need so much horsepower. Another item we can see on the nameplate is SF, or service factor. This safety factor is built into the motor insulation. It shows us how much amperage we can draw above the motor nameplate for short periods of time without insulation failure. So 31 amps multiplied by a 1.15 safety factor is as high as we can safely go for short periods of time without any major damage to this motor, 46.5 amps. It is not meant to run that way continuously, but for short periods it could be slightly overloaded. Last but not least is the power factor, or PF. We can see that the power factor of this motor is 81%, or 0.81. We can evaluate improving the power factor as an ECM for our motors. Remember, some tariffs may have a charge for poor power factor. Again, if we are going to do a desktop evaluation, we need to be able to read the nameplates on the motors we use. Pump horsepower requirements. We have provided a flow chart here where we have power coming from the power company with the power going to the motor where it equates to 1.54 horsepower. We call that motor horsepower. In other words, the power company is saying we have to give this system a 1.54 horsepower capability. Because of losses in the motor or inefficiency, we end up only sending 1.38 horsepower to the pump. This shows that we have lost some horsepower in that induction process, maybe in the coupling or in the drive. But we have lost some horsepower as a result of those devices. So now we are only delivering 1.38 horsepower to the pump. We call this the brake horsepower. Brake horsepower information is typically available on the pump curve. With this desktop small system approach evaluation, we will be looking at pump curves. Now, the 1.38 horsepower is delivered to the pump itself, and the pump in turn delivers this power to the water. We can see we transmit 1.38 brake horsepower to the pump. The pump has losses. It could be just the nature of the design, internal leakage, or recirculation waste power. As we can see in our pictorial, we only deliver 1 horsepower to the water. This flowchart shows us what goes on from our power company's perspective. This is the power they have to have ready for us. This is the power we are delivering to our water to move it, or air if it is air we're talking about. So it is motor horsepower, brake horsepower, water horsepower. Water horsepower is a theoretical value because it does not consider equipment efficiencies. Horsepower. At the top of this slide is the conversion. 1 horsepower equals 33,000 foot-pounds per minute. This guy named Watt had a horse, and his horse dragged 33,000 pounds, 1 foot, in 1 minute. And that is why we call it horsepower. What this tells you is that feet multiplied by pounds per minute equals horsepower. If we were climbing a set of steps, each one of us would use a different amount of horsepower because we each weigh different amounts, or pounds, and we move at a different speed, or time. But the height of the steps would be the same. If we each did this calculation of our horsepower, the results would be different. You can see that water horsepower is found by taking the flow in gallons per minute multiplied by the head and feet divided by 3,960. Where does the 3,960 come from? Remember, horsepower is feet multiplied by pounds per minute. We have gallons per minute, and we have feet in the top side of the formula. To convert flow in gallons per minute to pounds, we multiply the gallons per minute times 8.34 pounds to a gallon. So we put the 8.34 pounds per gallon in the top side of the formula, and we changed the 3,960 at the bottom to 33,000 foot-pounds per minute per horsepower. Now what we have is flow multiplied by head time, which is 8.34, divided by 33,000. We can shorten this formula because we have a constant in the numerator and denominator. If we divide 8.34 into 33,000, we get 3,960. So we don't have to use the 8.34 or 33,000 anymore. Therefore, if we are trying to figure out what horsepower a pump is going to use, all we need to know is flow and head. Now let's look at brake horsepower. Looking at the formula, what is the difference between brake horsepower and water horsepower? It is the pump efficiency. Brake horsepower is always going to be higher than water horsepower. Why is brake horsepower always going to be higher than water horsepower? The reason is because pumps are not 100% efficient. Any number less than 1 in the bottom half of our formula makes the result higher. Because pumps aren't 100% efficient, we are always going to have a higher brake horsepower than water horsepower. For our desktop evaluation, we are going to get the brake horsepower from the pump curve, which will be covered later. Finally, the motor horsepower. We can see this is the same formula as before, except it has added motor efficiency in the denominator. Motors are typically going to be 90 to 94% efficient or higher. Still, since they are not 100% efficient, motor horsepower is always going to be greater than brake horsepower. In this slide, we are using the pictorial values we saw on a previous slide as an example of just how we determine horsepower. We substituted real numbers in the formula using 100 gallons per minute and 39.6 feet of head as our criteria. Under these conditions, the result equals 1 water horsepower or 1 WHP. The reality is because of the inefficiency of the pump, we are actually going to use 1.39 brake horsepower because the pump efficiency is 72%. As we know, we have a motor to drive the pump, and we said the motor was 90% efficient. In this case, we filled in all the blanks and we come up with 1.54 motor horsepower. Horsepower with 1 foot increase in head. One of the energy conservation measures we want to consider is lowering pressure or lowering head in a pump system. Think back to what horsepower is. The key elements in horsepower are flow and head. If we change those elements, we change power. In this slide, we simply increase the head by 1 foot. Now we know that 1 foot of head is less than half a pound per square inch. If we have a water system at our plant and we are able to set the pressure, simply lowering target half a pound per square inch can save us energy. Let us run through the math. We increased the head by 1 foot. The results were 1.02 water horsepower, 1.42 brake horsepower, and 1.58 motor horsepower. If we look at the previous slide, we will see that there is a 2 to 4% increase in horsepower and energy, simply by increasing the pressure half a psi. So higher pressure or head means higher horsepower. What does that mean? It means we could possibly raise our wet well 1 foot or lower our pressure setting half a psi, and we could save 2 to 4% in energy cost simply by doing a process set point change. Do you have a plant water system? If you have a plant water system and it has an adjustable pressure setting, then you can consider this option. Also, think about how much water we waste in a plant water system. Treatment plants often have water running everywhere. That lower pressure will also mean less flow, an additional benefit and energy saver. In the water systems some of you operate, is it possible to lower the operating level on your storage tank or pressure in your hydropneumatic tank? Can you set the controls to lower pressure? Some areas to think about and evaluate. Why energy conservation? Why are we concerned about energy conservation? Per EPA, essentially 2% of all U.S. energy is used by water and wastewater systems. Think about the number of plants we have versus all the other things out there. We are big users of power. Approximately 35% of a utility's energy is used for water or wastewater treatment. Most of our utilities' energy costs are probably related to running our facilities. 15 to 30% of larger plants' wastewater treatment budget is for energy. For smaller plants, it can be even higher than that at 30 to 60%. There is a small water system down in a little town in Maryland which went from a regular conventional activated sludge type of process to an ENR process. When the town got their first electric bill, they were floored. The operator said to them, "Just come down and look at the generator we have. It is 5 times bigger than the one we had before." This plant is going to use a lot more power with ENR than they used with the regular process. They now have to consider that. Anything they can do to possibly save money is going to be a big deal. All of this translates to a large opportunity to save money. It is tough with ENR, but it is not impossible. Why is energy conservation important? According to EPA, aeration and pumping systems are the biggest part of our costs, no matter what we do, with aeration being by far the largest. As we mentioned earlier, aeration is fundamental to the process. We have to get nitrification before we even get denitrification. We can see that energy costs are a bigger percentage of the budgets for the smaller systems. Energy use and savings. A typical plant uses 1,200 to 2,500 kilowatt hour per million gallons. We want to see how our plant's energy use and savings are compared to a typical plant. It is also good to compare ourselves to what the typical standards are. Maybe we can start asking questions. Is it us, the design, or what is it? One of the things which will help us with monitoring energy use and savings are compiling some spreadsheets with baseline data on our system, so that we can track how we are doing and the impacts of what we have done. With advanced nutrient removal, we can expect 30 to 50% more energy consumption. If we are planning an upgrade, we should expect a significant increase in energy costs. How do we save energy? For this class's discussion, there are 3 ways to save energy. 1. Using a less expensive source. 2. Pay less for what you use. And 3. Use less power. Ultimately, some of this is out of our hands. A lot of municipalities are negotiating energy tariffs with their power supplier, so they can at least project energy costs. The less expensive source and pay less for what you use options are usually in the hands of the people handling those negotiations. So that leaves the option of using less power. The operator can strive to meet that third option of using less power. Less power means using energy efficient equipment and making operational modifications and process control enhancements. Those are primarily the 3 things that we can do to use less power, and this is where we will focus our efforts. The Plan, Do, Check, Act approach. This graphic is from the EPA manual in your class toolkit. What we have to realize is that energy conservation is not a one-day exercise. We cannot say we are going to cut the pressure back on plant water and just leave it at that. It is more involved than that. We have to follow through. Did it work? Is it amounting to anything? What is it hurting? What is it helping? We have to follow this process. We have to plan. we have to do, we have to check, and we have to act. This is a constant cycle. Just like we have to monitor and report on our permit to make sure we meet standards day after day, we are going to monitor and review our energy consumption. We need to have a plan for what we are going to do, and we have to follow through using the plan, do, check, act approach.